Climate change and its negative impacts. We're all aware of them by now. Carbon dioxide is at the forefront of the causes behind global warming and therefore an issue we must deal with. I am Tanmay Parikh and I am here today to talk about carbon capture and its use. With net zero commitments we made all across the globe, there are a plethora of different ways in which humanity is trying to reduce these emissions. The most fascinating to me being carbon capture. Carbon capture, utilization, and storage refers to a suite of technologies that can play a diverse role in meeting global energy and climate goals. It is a three-step process involving capturing the carbon dioxide produced by power generation or industrial activity, transporting it, and then either utilizing the carbon dioxide captured or storing it deep underground. The post-combustion capture of carbon dioxide is done by absorption processes, which work by contacting carbon dioxide with a solvent in an absorption column. There are around 35 commercial facilities currently implementing various such technologies using various solvents with a total annual capture capacity of 45 megatons of carbon dioxide. However, this needs to increase significantly and quickly. Even though research conducted by the International Energy Agency and the Intergovernmental Panel on Climate Change has shown that we need to implement these technologies on a global scale to mitigate climate change, the costs associated with the process prevent more industries from implementing it. Therefore, so it is also important to enhance this imperfect process. The most important challenge to subdue is to make the process economically feasible. Due to its high reactivity with carbon dioxide, monoethanolamine solvent has been used in carbon capture for many years. Once monoethanolamine, which is MEA, reacts with carbon dioxide to form a compound called carbamate, the energy required to separate CO2 from MEA so that the next phase of carbon capture, utilization, and storage can be carried out requires a lot of. The regeneration of spent MEA, which is desorption of carbon dioxide from MEA, requires carbamate to be exposed to temperatures of 150 to 180 degrees Celsius for 10 minutes in the solvent regeneration column. Obviously, for industries to even consider implementing this process would be fiscally irresponsible. So, it is necessary to either look for alternatives and give up on this process completely, or to somehow reduce the amount of energy required. Various alternatives are being researched constantly, even implemented at a large scale. CCUS has several variables which can be tweaked for better results, and thus the scope for improvement in efficiency and feasibility are wide. I would now like to speak about a project I undertook where at lab scale I managed to reduce the temperature required for regeneration of spent MEA from 150 to 180 degrees Celsius to a measly 60 degrees with the application of graphene ion nanoparticles. I've been deeply intrigued by nanoparticles and their properties for a while now. While researching, I came across a study which discussed the heat transfer from nanoparticles for the targeted destruction of iron. In the study, they described a phenomenon called the localized heat effect, whereupon heating a solution in which certain nanoparticles are randomly scattered cause the solution to be heated to elevated temperatures. Now, how does this happen? So, with these nanoparticles randomly scattered in the solution, when the solution gets heated, small regions surrounding these nanoparticles get heated to an elevated temperature. So even if we provide heat, which is not to the extent required to achieve temperatures of 150 or 180 degrees Celsius, you may still be able to reach those temperatures in these very small regions surrounding the nanoparticle. Connecting the dots after finding out about this property, I realized that the addition of nanoparticles could really help with solvent regeneration in carbon capture. There were also plenty of papers discussing the photothermal properties of certain nanoparticles. I found further examples of nanoparticles being used in cancer treatment, solar desalination, and more. I also realized that the nanoparticles being magnetic could allow easy separation from MEA, and that would remove the final hurdle into making this proper innovation, which could actually be implemented. After verifying the legitimacy of my thought process and seeking help and advice from an expert, I hypothesized that synthesized graphene ion nanocomposites capable of producing localized heat effect and showing super paramagnetism should allow regeneration of monoethanolamine at significantly lower temperatures. Soon, I acquired the necessary materials and started work at my father's laboratory. And to the best of my abilities, and to the best of the abilities of a 16-year-old with an extremely busy schedule, I conducted experiments. I constantly took help of the scientist acquaintances of my father to minimize errors and felt immensely rewarded when the results aligned with my hopes. By adding 20 milligrams of these nanoparticles to 200 milliliters of monoethanolamide, 100% regeneration was achieved at around 60 degrees Celsius. The highly reduced energy requirement due to drastically lower temperature requirements could potentially make CCUS feasible for a vastly increased number of industries. The nanoparticles could be magnetically separated and reused as well. Carbon dioxide capture, utilization, and storage has immense potential, and in my opinion, will play a major role in humanity's redemption and success in not letting our planet become uninhabitable. I hope even more smart minds around the world work towards innovating in this field and contribute towards a better environment for all of us to live. Thank you.